Previously, when we worked on the whole concept of work and energy, we talked about conservation of energy if there were conservative forces at work like gravity or spring forces. And we can still use conservation of energy to solve problems, but we have to keep in mind that now our objects will be rotating and translating. So as an example, let's assume that I've got an inclined plane, and instead of a block sliding down an inclined plane with no friction, let's consider a ball rolling down an inclined plane. So the ball will have a velocity in this direction, but it will also have an angular velocity, in this case in the clockwise direction. So we could set up an energy bar graph just like we did before, and let's take our datum to be here. So y is equal to 0 at this bottom location. And so we have some kinetic energy, but I'm going to separate now my kinetic energy into a translational kinetic energy and a rotational kinetic energy. And as before, we'll also have gravitational potential energy. So if the object starts from rest at the top, it's neither translating nor rotating, but it will have a certain amount of gravitational potential energy at the top. And then when it reaches the bottom, it will no longer have gravitational potential energy, but it will have kinetic energy, both translational and rotational. And I don't know which of these is larger. I'll just say the translational is in this specific example, but it doesn't really matter. And so you can see I have 3 blocks of total energy on the left and 3 blocks of total energy on the right. And I can put equations together with this. I have no translational kinetic energy. I have no rotational kinetic energy. But I do have a gravitational potential energy, mgh, where h is this height from the datum to the center of gravity. Okay, so that would actually be to the center of gravity. And then down here at the bottom, I have a translational kinetic energy, 1/2 mv squared, plus a rotational kinetic energy, 1/2 I omega squared, but no gravitational potential energy. Okay, and so that problem is ready to be solved. I don't know what I'm given and what I'm looking for, but that's the equation that I would set up to solve this problem. In this particular case, where I have a cabinet on wheels rolling down the inclined plane, I'm going to have rotational kinetic energy for each wheel and translational kinetic energy for each wheel, and then a translational kinetic energy for the cabinet. So in this case, the energy bar graph would be set up with 5 blocks or 5 slots for kinetic energy. T rotational 1, T translational 1, where there's wheel number 1, wheel number 2, so T rotational 2, T translational 2, and then just T translational for the cabinet. But then there's a gravitational potential energy as well. And I would have those same blocks of energy at the bottom. At the top, it would just have some potential energy, and then at the bottom, all these blocks would be distributed into these kinetic energies. All right, so let's take a look at this example. In this case, I have a rod AB, and it has a weight, so the mass of AB times G is equal to 8 pounds. And then there's a flywheel, and the flywheel has a weight of 32 pounds, and a radius of gyration about its center of gravity equal to 9 inches, which is 3/4 of a foot, or 0.75 feet. And of course this means that the flywheel has a moment of inertia about its center of gravity of 32 pounds divided by 32.2 feet per second squared, because we have to convert the weight into mass, times 0.75 feet, and that quantity is squared. In its current position, we're being told that it has a rotational velocity of 60 RPMs, so omega equals 60 RPMs, which is 2 pi times 60 radians per 60 seconds. And so this is 2 pi radians per second, and that's actually in the negative k direction. So this is the current position. AB is off at an angle here, and what we're interested in is what's the velocity of the flywheel when B is directly below C. And so in that scenario, the slider at A will have come down, and the bar will be straight up and down, so B will be down here, and the flywheel is centered, something like that. So this is the initial position here, and this is the final position over here. And so really the main change is that the gravitational center of the flywheel will have gone down. So in this scenario, I'm going to put the datum for the flywheel. I'm going to put the datum for the bar right here. So there's my datum for the bar. So that's y is equal to 0. So in the final position, gravitational potential energy will be 0. So I'm going to need to figure out what this height y is. So let's take a look at where things are in order to calculate that new position. So G is in the middle of the bar AB. This is 12 inches here and 36 inches here. And so I have triangle, 12 inches at the base. So let's just move that over here so I can get a better look. At 36 inches here, 12 inches here. And the center of gravity is in the middle of the bar, which will put it at the middle there. So what is my y distance? Well, 36 squared equals 12 squared plus L squared, where L is its total height there. So L squared is equal to 1152 inches squared. And so L is equal to 33.94 inches, or 2.83 feet. And so halfway up there, and again that's above C now, so it's half of that distance from C up to where the center of gravity is. And the bar is 36 inches tall, so from C to the center of gravity, you know this is 12 inches, so this must be 6 inches between these two. So the datum is 6 inches, which is a half a foot above C. And this distance, half of that distance, is the distance above C. So then we'll subtract a half a foot from there. So y would be equal to 1.414 feet minus a half a foot, which is 0.914 feet. So with that information, I can use this omega to calculate out the kinetic energy of the flywheel, this distance to calculate out potential energy of the bar. But what about the kinetic energy of the bar? How do we know the kinetic energy of the bar? It's moving, so there's translational kinetic energy for the bar, and there's rotational kinetic energy of the bar. But I can take note that B is moving straight up, tangent to the radius vector here from C to B, and A is moving straight up. And since those two velocities are parallel, and the bar is solid, meaning that it has to move together, then I can determine that the omega for AB at this current location is 0. Now the velocity is not the linear velocity, but omega is. But I can calculate out the linear velocity. Let's just go ahead and we'll prove that. Let's not just take it for granted. So I have a velocity of b with respect to c. Now c is a fixed point, and that's going to equal the position of b with respect to c. And that's going to equal omega of the flywheel crossed with the position of b with respect to c. And that's going to be 2 pi seconds to the minus 1. That's in the negative k direction, crossed with 1 foot in the negative I direction. So k cross I is j, minus and minus gives me a plus. So this is 2 pi feet per second in the j hat direction. Moving up makes a lot of sense, so that's okay. And then the velocity of A with respect to B equals omega AB. Let's just assume that that's in the positive k direction, crossed with the position of A with respect to B. And that's going to be I, j, k, 0, 0, omega AB, and then 1 foot in the I direction, because I'm going this way and then this way to get from B to A. And we've determined, remember, that this is 2.83 feet, or 2.83 feet in that direction, 0. And so when I calculate this out, I get minus 2.83 feet omega AB in the I hat direction, plus 1 foot omega AB in the j hat direction. And so the velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. And so I have minus 2.83 feet omega AB in the I direction plus 1 foot times omega AB in the j direction plus 2 pi feet per second in the j direction. Remember, A is fixed to be in the j direction, so the I component must be 0. This is the only I component, and so since minus 2.83 feet times omega AB must be 0, then that means that omega AB is equal to 0. So there's no rotational kinetic energy here. Now I can also find the velocity of G with respect to C. That's going to be the velocity of G with respect to B plus the velocity of B with respect to A plus the velocity of B with respect to C. But this is omega of the bar, AB, crossed with the position of G with respect to B. This is 0. And so all I'm going to have is the velocity of B with respect to C. And I know that that's 2 pi feet per second in the j hat direction. Okay, so my initial energy I'm going to have some translational kinetic energy for AB. A rotational kinetic energy for AB is going to be 0. I'm going to have some rotational kinetic energy for the flywheel, and I'm going to have some gravitational potential energy for the bar. So I can put in some numbers here. It's an 8-pound rod, so the mass is 8 pounds over 32.2 feet per second squared, and the velocity is 2 pi feet per second, that's squared. The rotational kinetic energy is 0. Then the flywheel has a moment of inertia, we call it 32 pounds over 32.2 feet per second squared, and 0.75 feet squared, times omega, which is 2 pi radians per second squared. And then the gravitational potential energy of the bar, which was mg, which is 8 pounds, times 8, which was 0.914 feet. So there's all my energy at the beginning. Same things at the end, except in this scenario, dB is 0. I still have translational kinetic energy for the bar, and rotational kinetic energy is a possibility. And of course, rotational kinetic energy for the flywheel. And so it might look something like this. Don't really know. The same number of bars on the left as I have on the right. So 1, 5, 7 there, 2, 3, 7 there. Now the number of bars on the left would be 1/2 8 pounds, 32.2 feet per second squared, times V of AB squared, plus 1/2 moment of inertia of the bar is 112, the mass 8 pounds over 32.2 feet per second squared, times 3 feet squared, times omega of bar AB squared, plus 1/2 32 pounds 32.2 feet per second squared, 0.75 feet squared, times moment of inertia of the flywheel, times omega of the flywheel squared. So I need to figure out what is the relationship between the omega of the flywheel and the omega and the velocity of the bar. Now keep in mind it's going to be down here in this position in that final scenario. So here's A, and here's B. And let's give the flywheel some omega. I don't know what it is, but I'll just call it omega F. And it's in the negative K direction, it's clockwise. And I can see that the wheel is going to be moving in this direction at its base. So the velocity of B with respect to C is going to equal minus 1 foot times omega of the flywheel in the I-hat direction. And then the velocity of A with respect to C is equal to the velocity of A with respect to B plus the velocity of B with respect to C. The velocity of A with respect to B will be omega of bar AB crossed with the position of A with respect to B, which is 3 feet in the J-hat direction. Omega AB will assume is in the positive K-hat direction. K cross J is minus I, so this will be minus 3 feet times omega AB in the I-hat direction. Now this term here is just the velocity of A with respect to B. So I have to add into that the velocity of B with respect to C. And so I'm going to get minus 3 feet omega AB in the I-hat direction plus the velocity of B with respect to C, which is minus 1 foot times omega of the flywheel in the I-hat direction. In this scenario, A is restricted to run only in the J direction. So this total velocity has to be 0. And therefore, 3 times omega AB equals minus 1 times omega F, where the feet are canceled out here. And I brought it to one of these the other side, so this has gone to positive and that stays negative. But what that means then also is that the velocity of A is 0, because there is no J component anywhere in this equation. If the velocity of A is equal to 0, I can similarly find out 3 omega AB is omega F. This will also turn out to tell me that the velocity of G in this position is also equal to 0. So there is no translational kinetic energy for bar AB in this downward position. And I also know the relationship between omega the flywheel and omega AB. So the right-hand side of that energy equation, okay, we take a look back at this equation. I know everything here on the left. That's all known. On the right-hand side, I've determined that that's going to go away. There is no linear velocity. And I now know the relationship between omega AB and omega F. And so the only unknown, if I write omega AB in here as 1/3 omega F, then the only unknown on the right-hand side is omega F. and I can solve for the angular velocity of the flywheel, which is what I'm looking for.